Hello, and thank you for joining me on this gentle journey. Tonight, we will slowly drift into the mysterious world of oil, formed deep within the earth over millions of years. Imagine tiny plankton and algae settling into ancient seabeds, layered under soft sediments, slowly transforming under heat and pressure into dark, flowing liquid energy. Picture the subtle shimmer of oil hidden in rock, a treasure shaped by time itself, influencing civilizations, technology, and even the little comforts of daily life. Let your awareness float along these slow, natural processes, feeling the warmth of the earth, the quiet hum of ancient seas, and the gentle rhythm of creation beneath your feet. If you enjoy these relaxing moments, please consider leaving a like, subscribing, and turning on all notifications so you don't miss any of our future videos. But for now, just breathe. Let your body relax, release any tension, and allow your mind to drift. Let's begin. Deep beneath layers of ancient sediment, microscopic plankton from millions of years ago slowly transformed into viscous hydrocarbons, compressed and heated under immense pressure. A quiet reminder that the energy powering modern life was born in oceans long vanished from the Earth's surface. These primordial remains, once drifting freely in sunlit waters, became a concentrated reservoir of chemical potential, waiting patiently for humanity's ingenuity to reveal their latent power, encapsulated in the Earth's secret chambers. In some remote deserts, traces of seeped hydrocarbons have stained rock formations for millennia, a testament to the slow percolation of subterranean fluids. Nomadic peoples once discovered these sticky residues, using them for waterproofing containers or rudimentary adhesives, unaware that these remnants foreshadowed the monumental energy revolutions to come, connecting natural processes to human curiosity and practical innovation long before the first industrial wells punctured the Earth's surface with mechanical precision. Certain geological formations, like anticlines and salt domes, create natural traps for dense fluids, where light hydrocarbons float above heavier fractions. These invisible pockets act as hidden vaults, storing immense quantities of concentrated energy that can lie undisturbed for eons. Geologists mapping these contours with seismic echoes uncover not only reservoirs, but stories of tectonic shifts and ancient ocean currents, revealing a deep interplay between Earth's movements and the accumulation of concentrated organic remnants. The chemical fingerprints of these ancient molecules reveal surprising complexity. Long chains of hydrogen and carbon twist into aromatic rings, alkanes, and other structures that determine everything from viscosity to combustibility. Slight variations in these molecular arrangements can change the color, texture, and burning properties of the resource entirely. Spectroscopy and chromatography allow scientists to read these molecular signatures like a diary, unlocking secrets of Earth's biological and chemical past, layer by layer. In early civilizations, bituminous deposits were often revered for their transformative qualities. Mesopotamian builders used sticky tar for fortifying walls and waterproofing boats, while Egyptian artisans incorporated natural pitch in embalming rituals. These practical and ceremonial applications show that humans recognized unique energy and chemical properties long before mechanical extraction, blending utility with reverence and intertwining cultural history with the quiet flow of these dense ancient compounds. Under high-pressure geological conditions, certain microorganisms contribute to the breakdown of organic matter, releasing methane and other gaseous byproducts. These processes, occurring slowly over millennia, create natural variations in chemical composition that later influence refining strategies. Modern scientists trace these microbial signatures to understand regional differences in fluid quality, uncovering a hidden biological dimension to what might seem purely geological, illustrating that life and Earth's chemistry continue an intricate dialogue beneath our feet. Some reservoirs contain lighter fractions that behave almost like water, seeping into porous rocks and sometimes surfacing as small seeps in rivers or marshlands. Observers throughout history noted these occurrences, often attributing supernatural qualities to bubbling tar or flaming gases igniting from natural vents. Today, these seeps inform exploration strategies, indicating subsurface abundance while offering a living snapshot of ancient biochemical processes, bridging observation, folklore, and contemporary geology in a single, flowing narrative. The refining of these dense compounds transforms a dark, viscous fluid into multiple functional products, from fuels to lubricants to plastics. Fractional distillation separates molecular chains according to volatility, while catalytic reactions modify structures for specific applications. This conversion, though highly technical, echoes nature's own selective processes, imitating millions of years of chemical evolution compressed into hours. The result is a cascade of functional materials that shape modern society, all stemming from microscopic life forms of the distant past. Transporting refined products historically required ingenuity. Wooden barrels, steel pipelines, and even camel caravans were adapted to contain the volatile, flammable liquids. Leaks or spills were early lessons in risk and adaptation, prompting gradual improvements in infrastructure. These logistical solutions became intertwined with trade, warfare, and industrial expansion, demonstrating that the movement of this concentrated energy has always been as much about human organization and ingenuity as it is about chemical transformation beneath the Earth's crust. The visual contrast between light, golden fractions and dark, dense residues in refining columns is striking, resembling layered sunsets frozen in motion. Observers note the almost liquid artistry of this separation, where heat and pressure coax molecules to rise, condense, and fall in carefully choreographed patterns. Beyond functional necessity, this spectacle reveals the hidden beauty in chemical physics, where manipulation of molecular weight and volatility transforms an opaque, inert mass into a palette of usable, tangible products. In some regions, ancient oil-rich deposits influenced human settlement patterns, as the fluid was a source of waterproofing, fuel for lamps, and even primitive medicine. Archaeologists find evidence of trade networks forming around such resources, suggesting that the concentration of hydrocarbons subtly shaped civilization's growth. These intersections of geology, chemistry, and sociology illuminate a less obvious dimension of human history. Energy resources quietly guiding societal development long before industrial technology could fully exploit their potential. Natural seeps can also ignite spontaneously when gases accumulate and find an ignition source, creating long-burning flames that fascinated explorers. Some of these eternal flames became sacred sites, inspiring myths of divine fire or celestial phenomena. Today, geologists study these events to understand subsurface pressures and gas migration patterns, turning folklore into a scientific narrative where ancient human imagination meets precise geophysical measurement and the ethereal glow of combustion serves as a reminder of the Earth's persistent hidden energy. Certain heavy residues, known for their tar-like consistency, resist oxidation and biological decay, persisting for centuries even in open environments. These materials reveal the endurance of carbon-rich compounds and their resistance to environmental breakdown, offering insight into molecular stability and potential. Applications in coatings, construction, and industrial materials. Their longevity contrasts with lighter fractions, highlighting the diverse behavior of chemical structures derived from the same biological origin, and reinforcing the complexity hidden in a single, seemingly simple substance. Hydrocarbon migration occurs slowly, sometimes over kilometers, as fluids navigate through rock fractures, porous sediments, and fault lines. These journeys, driven by buoyancy and pressure differences, form accumulations in unexpected locations, often discovered after careful seismic mapping. Understanding these movements illuminates both the randomness and the predictability of subsurface energy flows, revealing a hidden choreography dictated by Earth's structure, fluid properties, and geological history. A silent ballet beneath our feet. Fossil fuel formation preserves microscopic traces of past climates, salinity, and ocean currents. Scientists decode these chemical fossils to reconstruct Earth's ancient environments, reading subtle isotopic ratios as a chronicle of temperature, sea level, and biological productivity. Each sample serves as a time capsule, revealing how energy-rich deposits are more than just fuel. They are narratives of planetary history, holding stories of extinction events, algal blooms, and the subtle interplay of life and lithosphere over hundreds of millions of years. In modern laboratories, researchers explore bio-inspired alternatives by studying molecular structures of hydrocarbons. By mimicking natural chemical bonds and chain lengths, scientists attempt to produce synthetic analogues with fewer impurities or lower environmental impact. This convergence of chemistry, engineering, and environmental awareness reflects humanity's desire to harness ancient processes while mitigating consequences, transforming the study of natural deposits into a platform for innovation that balances utility with planetary stewardship. Some ancient oil reserves exist beneath extreme environments, from frozen tundras to deep marine basins, requiring advanced technology to access. Ice-bound regions challenge traditional drilling methods, while subsea reservoirs demand precise engineering under immense pressure. These extreme locales highlight human determination to reach previously inaccessible energy, demonstrating how curiosity, risk, and technological ingenuity extend the reach of civilization into some of Earth's most forbidding landscapes. Petroleum has even influenced art and literature. Painters captured the sheen of black tar on wetlands, while writers wove the allure and danger of hidden energy into narratives of discovery, conquest, and industrial might. These cultural artifacts reflect humanity's fascination with transformation, from natural viscous fluid to refined fuel, and reveal how energy resources resonate beyond science and economy, entering the subconscious imagination as symbols of power, wealth, and mystery. Early exploration maps often marked seeps with cryptic symbols, hinting at potential wealth buried underground. Cartographers relied on local knowledge, surface indications, and geological intuition to guide early drilling endeavors. These maps became instruments of both science and speculation, blending empirical observation with human ambition. The marks that once guided pioneers now inform modern geoscience, tracing the evolution of exploration from rudimentary sketches to sophisticated, computer-modeled subsurface imagery. Microbial activity in reservoirs can create unexpected chemical diversity, producing small amounts of hydrogen sulfide or altering viscosity. Such processes, though invisible, influence extraction methods, pipeline safety, and refining strategies. The dynamic interaction between microbes and hydrocarbons demonstrates that even ancient deposits remain biologically active under certain conditions, blurring the line between living systems and mineralized energy, reminding us that Earth's hidden landscapes are not inert, but constantly evolving. Some seeps were historically exploited as sources of natural asphalt for paving roads and waterproofing roofs. The same material that once coated ancient boats and shelters evolved into modern infrastructure, illustrating continuity of use across millennia. Observing the long-lasting utility of these dense residues highlights how natural processes inadvertently prepared humanity with resources, long before industrial chemistry enabled large-scale modification, providing both functional and symbolic value to communities living alongside these mysterious black veins. Beneath arid plains, ancient marine basins once teemed with microscopic algae, whose organic remains, compressed under layers of sediment, formed dense hydrocarbon deposits. Over millions of years, heat and pressure transformed these minuscule organisms into a thick, energy-rich substance that, when discovered, revealed the invisible labor of Earth's slow chemical artistry and hinted at the interconnected history of life, geology, and human ingenuity, drawn to harness its latent potential. Volcanic activity sometimes alters the surrounding rock of subsurface deposits, introducing minerals and gases that subtly shift the chemical composition. These interactions can influence color, viscosity, and even ignition tendencies. Scientists study mineral associations to trace the journey of these compounds through time, revealing that subterranean energy reservoirs are not static containers, but dynamic landscapes shaped by tectonic upheavals and molten intrusions from deep within the planet. Explorers in the 19th century often stumbled upon natural seepages, noticing flammable liquids bubbling to the surface. Local populations used these seeps for lamp fuel or sealing vessels, bridging observation with practicality. These early encounters, predating industrial drilling, highlight the intuitive human connection to natural resources as societies learned to interpret subtle environmental cues, guiding settlement, trade, and the nascent stages of energy exploitation. Some molecular chains trapped beneath layers of rock resist chemical breakdown, forming bitumen with extraordinary longevity. This durable substance has been found preserved for tens of millions of years, providing clues to ancient climates and sedimentary conditions. By analyzing its molecular fingerprints, geochemists reconstruct the environmental context in which these deposits formed, unveiling narratives of prehistoric oceans, fluctuating temperatures, and the complex interplay of biological and geological forces over deep time. Certain estuarine regions preserve hydrocarbon residues in sediments where decaying vegetation combined with tidal influences. These deposits often display layered stratification, each layer recording the rise and fall of sea levels, freshwater influx, and shifts in organic productivity. Geologists interpret these sequences to understand both the accumulation of energy-dense compounds and the subtle environmental changes that shaped coastal ecosystems, revealing how long-buried sediments silently archive Earth's ancient rhythms. Remote offshore basins can contain reservoirs located several kilometers beneath the seafloor, concealed within porous sandstone capped by impermeable shale. Acoustic waves generated by seismic surveys reveal their contours, allowing precise drilling. These underwater vaults illustrate the ingenuity required to locate energy sources that have remained untouched for millennia, demonstrating a careful balance between technological sophistication and the patient observation of geological indicators that nature laid down over eons. Ancient forests buried by sudden sedimentation events contributed massive organic matter that later formed viscous deposits. These catastrophic floods preserved tree trunks, leaves, and soil, creating concentrated pockets of hydrocarbons. By studying fossilized plant matter within these deposits, paleobotanists can reconstruct the appearance, climate, and biodiversity of long-lost ecosystems, highlighting the intricate connections between surface life, catastrophic events, and the energy reservoirs hidden beneath layers of time-worn rock. The color variation in dense hydrocarbons reveals subtle chemical differences. Light amber fractions indicate shorter hydrocarbon chains, while deep black residues suggest heavier, more complex molecules. Laboratory analysis of these differences informs refining strategies, predicting combustion efficiency and lubrication properties. Such observation transforms a seemingly uniform dark substance into a rich narrative of chemical diversity, linking molecular structure with practical human applications and the hidden history encoded in its composition. Some historical trade routes developed around naturally occurring asphalt deposits used for waterproofing ships. Ancient civilizations, including Phoenicians and Egyptians, exploited these resources to extend voyages, fortify vessels, and protect goods. This practical utility intertwined with commerce, technology, and exploration, demonstrating that deposits beneath the earth were not mere curiosities, but central actors in shaping early economic networks, cultural exchange, and maritime ingenuity. Gas bubbles trapped in ancient formations can create dramatic surface phenomena when released. Methane or hydrogen sulfide escaping through fractures may ignite spontaneously, producing flames that astonished observers for centuries. These occurrences inspired myths of eternal fire or divine intervention, while modern geologists interpret them as indicators of subsurface pressure dynamics, gas composition, and migration paths. The spectacle reflects both the power of hidden natural forces and humanity's historical tendency to attribute meaning to environmental surprises. In deep sedimentary basins, overpressure can create fluid migration along faults and fractures, redistributing hydrocarbons over extensive areas. This slow movement shapes the distribution of energy-rich deposits, sometimes concentrating them in zones unexpected by early prospectors. Studying the orientation and connectivity of rock layers reveals the hidden corridors that guide these fluids, demonstrating how the Earth's structural architecture governs the accumulation of resources and the intricate pathways of ancient organic remnants. Ancient lakes, once rich with microscopic life, contributed significant organic matter that later transformed into energy-dense liquids. As sediments slowly buried this material, chemical reactions removed oxygen and preserved carbon-rich compounds. Analyzing these lacustrine deposits allows scientists to reconstruct water chemistry, temperature fluctuations and biological productivity of vanished lakes, creating a molecular window into Earth's prehistoric environments, and linking hydrological cycles to deep carbon reservoirs stored for millions of years. Crude extraction methods evolved from hand-dug pits to sophisticated rotary drilling, each iteration reflecting lessons learned from prior failures. Early wells often relied on natural pressure to bring fluid to the surface, while modern rigs employ advanced pumping and directional drilling. This technological evolution mirrors humanity's ongoing dialogue with hidden resources, demonstrating the interplay of engineering, geology, and ingenuity needed to convert deep reserves into accessible energy. Some aromatic hydrocarbons found in subsurface deposits were derived from ancient planktonic organisms that thrived in sunlit surface waters. When buried and subjected to heat and pressure, these molecules formed complex rings that affect combustion properties and refine into specialized products. Their persistence over geologic time offers chemists a window into the microscopic life of oceans long vanished, revealing both biological diversity and the chemical fingerprints left by evolutionary processes encoded in buried energy. In extreme desert regions, surface seeps sometimes create blackened crusts on the ground, where evaporation concentrates sticky residues. Locals historically used these for primitive waterproofing, while travelers noted their peculiar smell and texture. Studying these formations reveals subtle climatic interactions, including evaporation rates, sediment composition, and microbial colonization, demonstrating that even exposed deposits contain valuable information about surface processes, environmental conditions, and human adaptation across centuries. The viscosity of hydrocarbons increases with depth and time under pressure, giving rise to tar-like residues in certain formations. These dense materials resist flow and chemical alteration, making them both challenging to extract and fascinating for scientific study. Understanding their rheological behavior informs drilling techniques, material applications, and the interpretation of depositional environments, illustrating the diverse characteristics that naturally formed organic compounds can exhibit over geological timescales. Certain underground reservoirs contain natural gas caps that exert pressure on underlying liquids, assisting in extraction. The coexistence of gaseous and liquid hydrocarbons in stratified layers demonstrates the delicate balance of buoyancy, density, and cap rock integrity. Studying these systems allows engineers to optimize recovery while preventing hazards such as blowouts, and geologists to map migration patterns, revealing a complex subterranean equilibrium that has evolved over millions of years. Ancient oil-bearing shales can preserve fossilized microorganisms within their layers, offering a microscopic record of prehistoric life. By examining these inclusions, scientists gain insight into early biodiversity, microbial ecology, and nutrient cycles that contributed to organic accumulation. These microscopic time capsules transform seemingly inert rock into a living archive, bridging deep Earth chemistry with biological evolution and demonstrating the intricate connections between life and energy stored beneath the surface. Some hydrocarbons contain naturally occurring sulfur compounds, producing distinct odors and chemical behaviors. These trace elements influence refining, combustion, and corrosion characteristics, requiring careful handling. By analyzing sulfur content, geologists can trace depositional environments and biological origins, providing clues to the chemistry of ancient seas and wetlands. The subtle presence of such elements reveals the layered complexity of what might appear to be a simple, uniform substance, underscoring the chemical storytelling embedded in these reservoirs. Natural asphalt lakes, such as those found in specific tropical regions, support unique ecosystems where plant life and microbial colonies adapt to high concentrations of viscous hydrocarbons. These unusual environments illustrate resilience, adaptation, and co-evolution in extreme chemical conditions. Scientists study such sites to understand how life persists amid high toxicity, uncovering potential applications in bioremediation and offering a window into the interplay between living organisms and concentrated energy sources preserved for millions of years. Historical records reveal that ancient engineers sometimes used hydrocarbon-based pitch to insulate and waterproof monumental architecture. From roofing temples to sealing aqueducts, these materials provided both functional and symbolic value, demonstrating early recognition of their protective qualities. These practices underscore the versatility of naturally occurring hydrocarbons and how human ingenuity translated the hidden properties of ancient organic deposits into practical applications, shaping the built environment for centuries. Dark, viscous streams occasionally ooze through fractured rock in mountainous regions, leaving streaks that glisten under sunlight. These slow-moving flows are remnants of ancient organic material transformed under pressure over millions of years. Observing their patterns and chemical composition provides geologists with clues about the movement of fluids underground, the mineral interactions along their pathways, and the subtle variations in molecular weight that define their physical and industrial properties. Tiny voids within sandstone sometimes host pockets of dense liquid, sealed over eons by layers of clay and silt. These natural reservoirs act as storage chambers, preserving energy-rich compounds until discovered. Studying the texture, porosity, and mineral composition of these host rocks allows scientists to reconstruct burial histories and understand how sedimentary environments concentrate organic matter into distinct zones suitable for extraction. In coastal marshes, sticky black substances occasionally surface where ancient tidal channels once deposited plant matter. Over centuries, exposure to air and microbial activity alters the material's color and consistency. These surface expressions, while hazardous to handle, serve as natural laboratories, revealing chemical fingerprints of past ecosystems and offering insight into the relationship between tidal dynamics, sediment accumulation, and long-term organic preservation. Certain heavy oils contain intricate chains of carbon and hydrogen twisted into complex ring structures. These molecules resist flow and chemical degradation, making them difficult to refine yet valuable for specific industrial applications. Spectroscopic analysis of these chains provides scientists with information about the types of ancient organisms that contributed to their formation and the thermal conditions that influence their chemical evolution over millions of years. Bubbling seeps in desert plains sometimes ignite spontaneously, creating short-lived flames that rise above cracked ground. These natural ignitions occur when volatile gases accumulate beneath impermeable surfaces and reach an ignition threshold. Observers historically interpreted them as mystical phenomena, but modern analysis links them to subsurface pressure, fluid composition, and environmental conditions, illustrating how physical and chemical factors combine to create dramatic surface expressions of deep energy. Layered bitumen deposits within sedimentary rocks can preserve microscopic structures reminiscent of ancient plankton and algae. These remnants allow geochemists to trace the origin of the organic material and reconstruct the productivity of prehistoric oceans. By examining isotopic ratios and molecular arrangements, researchers gain insight into the environmental conditions that favored preservation, bridging the gap between microscopic life forms and the formation of concentrated energy reservoirs underground. Some oil-rich formations are capped by salt domes, creating natural barriers that trap viscous fluids below. These geological features can stretch for kilometers and often influence the migration path of petroleum, redirecting fluids into pockets of high concentration. Studying dome geometry, fracture orientation, and surrounding rock properties provides engineers with valuable information about potential recovery efficiency and reservoir stability. Volcanic intrusions near petroleum-bearing layers can alter both temperature and chemical composition. The heat can crack heavier molecules into lighter fractions or introduce trace minerals that influence reactivity. Examining these modifications allows geoscientists to interpret ancient thermal events, the timing of deposition, and the interplay between organic matter and surrounding mineral layers, revealing the chemical evolution of energy-rich reserves over geological time. Some offshore seep sites produce floating mats of thick black fluid that slowly drift with ocean currents. These mats create unique habitats for microorganisms that metabolize hydrocarbons, sustaining mini ecosystems independent of sunlight. Observing these drifting surfaces provides insight into microbial adaptation, the durability of complex molecules in marine conditions, and the transport mechanisms that redistribute natural energy-rich substances across vast distances. Ancient river valleys sometimes contain lenses of highly viscous crude trapped between layers of sand and clay. These pockets vary widely in chemical composition, influenced by the original vegetation and sedimentation patterns. Modern imaging and drilling techniques reveal the intricate architecture of these reservoirs, demonstrating how hydrodynamic forces, sediment deposition, and organic accumulation interact to create energy-rich zones suitable for exploration. In some regions, petroleum shows remarkable color variation from golden amber to near black, reflecting molecular weight and chemical diversity. Light fractions contain shorter chains that flow easily, while heavier compounds form dense, sticky material. This variation affects industrial use, refining strategy and combustion properties, transforming a single geological formation into a complex palette of functional substances shaped by millions of years of chemical transformation. High-pressure gas caps overlying dense liquids exert force that can drive flow through porous rock, sometimes bringing crude to the surface naturally. These self-pressurized systems demonstrate how geological confinement preserves energy and allows extraction without mechanical assistance. Understanding the balance of pressure, rock strength, and fluid properties is critical for safe production and for predicting the behavior of reservoirs over geological time. Some bitumen-rich sediments exhibit unique microstructures, preserving organic remnants that date back hundreds of millions of years. Microscopic examination reveals evidence of ancient microbial life, sediment deposition patterns, and chemical transformations that occurred during burial. These tiny structures serve as archives, connecting the chemical history of energy-rich compounds to the ecological conditions of distant prehistoric landscapes. Certain petroleum-bearing formations display striking layering, with lighter fluids migrating upward while denser fractions settle below. These natural separations mimic industrial distillation, influencing extraction and refining strategies. Analyzing stratification provides insight into the history of fluid movement, the properties of source material, and the impact of burial conditions on the eventual composition of energy-rich reserves. Some shallow seeps in coastal regions produce volatile compounds that evaporate, leaving thick, tar-like residues. These surface manifestations offer clues to subsurface composition, reservoir size, and migration pathways. Studying the distribution and chemical properties of these residues allows scientists to understand both the dynamics of fluid flow underground and the interactions between petroleum and environmental factors at the Earth's surface. Heavy petroleum fractions often resist microbial decay, remaining chemically stable for millions of years. Their persistence enables the study of ancient organic sources and thermal conditions during burial. By examining molecular architecture and isotopic composition, researchers reconstruct the environment in which these materials formed, linking chemistry to paleoclimate, sedimentation patterns, and biological productivity. Some petroleum reservoirs are associated with ancient reef structures, where porous carbonate frameworks trap dense liquids. These natural traps preserve both energy and fossils of reef-building organisms. Analyzing these formations allows geoscientists to interpret past marine ecosystems, sedimentation patterns, and the interaction of biology and geology in creating concentrated subterranean energy stores. In certain offshore basins, natural asphalt occasionally surfaces, coating marine sediments and creating habitats for specialized organisms. Microbes that metabolize hydrocarbons flourish in these extreme environments, demonstrating adaptability to chemically challenging conditions. Observing these interactions provides insight into both the longevity of petroleum compounds and the ecological processes that allow life to coexist with concentrated organic material. Historical evidence shows that early engineers used bitumen for waterproofing boats, fortifying structures, and sealing containers. These applications reflect practical knowledge of material properties derived from natural energy-rich deposits centuries before industrial extraction. The enduring utility of these compounds demonstrates how their chemical and physical characteristics were harnessed in both functional and cultural contexts across time. Some deep reservoirs contain sulfur-rich hydrocarbons, which affect odor, combustion, and corrosion behavior. The sulfur content varies with depositional environment and biological origin, providing clues to ancient ocean chemistry and sedimentation conditions. Studying these variations informs refining methods and safety considerations, revealing that chemical diversity within energy-rich fluids encodes a geological and biological record preserved over millions of years. Occasionally, thick black veins of crude are exposed in canyon walls, where erosion has cut deep into sedimentary layers. Observers can see streaks and glimmers reflecting sunlight, revealing the slow seepage of fluid that migrated through rock over millions of years. Geologists study these exposures to infer reservoir size, migration pathways, and the chemical composition shaped by thermal history and surrounding mineral interactions. Some offshore basins hold reservoirs buried beneath kilometers of mud and shale, where extreme pressure slowly transforms trapped organic material. These deep formations may contain fluids of differing densities and chemical compositions, creating stratified layers. Understanding the dynamics of these deep systems requires seismic imaging, pressure modeling, and chemical analysis, which together reveal how ancient marine ecosystems became locked into dense energy stores far below the seabed. Viscous black matter sometimes accumulates in depressions along riverbeds where ancient flood events trapped plant debris. Over geologic time, compaction and heat transform these remnants into dense, energy-rich material. By examining fossilized plant fragments within these deposits, paleobotanists can reconstruct climate, vegetation types, and flood dynamics, showing how surface events millions of years ago influenced the formation of hidden energy resources. Certain petroleum-rich formations are capped by impermeable layers of shale or clay, forming natural reservoirs under immense pressure. These seals prevent fluid escape and create pockets that can remain stable for tens of millions of years. Geologists study the integrity and thickness of cap rocks to predict reservoir longevity, extraction safety, and the potential for natural seepage that shapes surface environments over time. Some ancient coastal plains preserve black, sticky residues where tidal cycles concentrated organic matter. These remnants show layering of silt, sand, and plant debris, capturing snapshots of long-gone ecosystems. By analyzing chemical composition and isotopic ratios, scientists can infer vegetation types, salinity levels, and sedimentation patterns, transforming these deposits into archives of environmental change and the slow accumulation of energy-rich compounds. Tiny gas bubbles trapped in deep formations occasionally escape along fractures, sometimes creating small fiery displays when mixed with oxygen. Historically, such phenomena inspired myths of eternal flame or divine intervention. Modern science interprets these occurrences as indicators of subsurface pressure, chemical composition, and the mobility of natural gases, illustrating the dynamic nature of deep earth energy reservoirs. Heavy residues preserved in deep rock layers resist chemical breakdown and microbial attack. Their stability allows geochemists to study ancient molecular structures and trace the original biological sources. These compounds reveal thermal histories, burial conditions, and the types of organisms that contributed to their formation, connecting microscopic life from millions of years ago to the concentrated energy that humans exploit today. Some petroleum-bearing shales formed in oxygen-poor lakes, where organic material settled undisturbed for millennia. The lack of oxygen prevented decomposition, allowing preservation of dense, energy-rich compounds. Detailed study of these shales provides insight into ancient water chemistry, sediment accumulation rates, and the conditions that favored organic concentration, revealing the interplay of biology and geology in shaping subterranean reservoirs. Certain underground reservoirs exhibit stratification where lighter hydrocarbons float above denser, more viscous layers. This natural segregation influences extraction techniques, as fluids of different densities respond differently to pressure changes. Geoscientists study these layers to reconstruct migration histories, assess fluid composition, and predict reservoir behavior, highlighting the subtle physical sorting that occurs deep within sedimentary basins over millions of years. Some natural asphalt lakes host microbial colonies capable of metabolizing complex hydrocarbons. These microorganisms survive in extreme chemical conditions, forming localized nutrient cycles. Studying such ecosystems informs bioremediation and reveals how energy-rich compounds interact with biology over long timescales. These environments showcase the resilience of life in chemically hostile habitats and the ecological impact of concentrated subterranean energy when exposed at the surface. In regions with historical tectonic activity, fractures in rock can redirect migrating hydrocarbons, concentrating them in pockets far from their original deposition. These fault-guided reservoirs demonstrate how structural geology shapes energy distribution. By mapping fracture orientation, mineral content, and fluid movement, geologists gain insight into the interplay between tectonics, fluid dynamics, and organic accumulation that determines the location of exploitable reservoirs. Some heavy oils contain complex sulfur compounds that influence color, odor, and reactivity. Variations in sulfur content often reflect the depositional environment of the original organic material. Analyzing these chemical signatures allows researchers to infer past ocean chemistry, biological activity, and sedimentation patterns, turning energy-rich fluids into chemical archives of Earth's ancient environmental conditions. Ancient river deltas sometimes hold lenses of viscous crude that accumulated where currents slowed and deposited dense organic material. These pockets provide insight into sediment transport, floodplain evolution, and plant productivity millions of years ago. Examining these formations reveals how subtle changes in hydrodynamics influence the creation of concentrated energy zones beneath present-day landscapes. Occasionally, crude emerging at the surface reacts with oxygen and water to form thick black crusts. These weathered layers record the exposure history, microbial interactions, and evaporation effects over decades or centuries. Scientists study these crusts to understand surface expression of deep energy reservoirs, fluid migration patterns, and chemical evolution from source rock to exposed layer. Petroleum trapped in fractured carbonate formations can create highly irregular reservoirs with variable porosity and fluid composition. Extraction requires precise mapping and modeling to avoid inefficient recovery. Studying these formations shows how sedimentary environments, tectonic stress, and chemical reactions work together over geological time to produce reservoirs with diverse physical and chemical properties. Some offshore hydrocarbon seeps form temporary floating mats that drift along currents, carrying viscous material across hundreds of kilometers. Microbes colonize these mats, metabolizing hydrocarbons and creating micro-ecosystems. Observing their movement offers insight into oceanic fluid transport, chemical weathering, and the interaction of biology with energy-rich compounds outside traditional reservoir confines. Certain petroleum deposits formed in ancient swamp systems, where thick vegetation accumulated and decayed under stagnant water. Burial under sediment preserved the organic matter, later transforming into dense liquid. Fossil evidence within these deposits allows reconstruction of paleoecology, climate, and hydrology, connecting terrestrial ecosystems with the eventual formation of subterranean energy resources. High-pressure gas caps over liquid reservoirs can naturally drive fluids to the surface through narrow channels. This mechanism illustrates the balance between fluid density, pressure, and permeability, which governs natural movement over millions of years. Engineers must understand these dynamics to safely manage extraction and predict reservoir behavior during production. Some natural asphalt formations have persisted for tens of thousands of years, creating stable, sticky surfaces on land. These sites host adapted microbial life and preserve chemical signatures of their organic origins. Studying them provides insight into long-term chemical stability, microbial adaptation, and the interaction of energy-rich compounds with surface environments. Crude extracted from ancient reef-associated formations often contains fossil fragments embedded in the viscous material. These inclusions provide paleontological insights while revealing how organic matter concentrated in porous skeletal frameworks. By examining fossil distribution, scientists reconstruct both ancient ecosystems and the structural traps that facilitated long-term preservation of liquid energy reservoirs. In some deep marine basins, hydrocarbons accumulate where ancient plankton blooms were buried rapidly under fine-grained sediment. These fluids retain chemical markers of ocean productivity, including lipid remnants and isotopic ratios, allowing scientists to reconstruct ancient nutrient cycles. By examining molecular fingerprints, geochemists can infer the abundance and diversity of microscopic life that contributed to the energy stored in these hidden reservoirs, connecting deep chemistry to vanished ecosystems. Viscous petroleum sometimes migrates along the boundaries of folded rock layers, forming pockets where porosity and permeability allow accumulation. The subtle curvature of these formations directs fluid flow, concentrating energy-rich liquids in unexpected locations. Studying these patterns helps geologists predict where reservoirs may exist, revealing the delicate interplay of structural deformation, sedimentary architecture, and organic concentration that governs the subsurface distribution of natural resources. Bitumen preserved in desert sediments sometimes contains fine plant fragments that escaped complete decomposition. These remnants reveal the species composition and environmental conditions of prehistoric landscapes. Through careful chemical and microscopic analysis, researchers can reconstruct temperature fluctuations, soil composition, and vegetative productivity, transforming what appears to be inert black matter into a rich archive of ecological and geological history. In certain offshore locations, black asphalt occasionally surfaces in slow-moving patches that resemble floating mats. Currents transport these mats across marine environments, while chemical weathering slowly modifies their composition. Microbes capable of metabolizing hydrocarbons inhabit these surfaces, creating micro-ecosystems that thrive independent of sunlight. Studying these phenomena provides insight into the resilience of life and the persistence of energy-rich compounds outside of confined geological reservoirs. Heavy fractions of crude sometimes crystallize into waxy forms within reservoirs, resisting flow until heated or diluted. These crystallized structures provide clues about thermal history, burial depth, and molecular composition. Examining their formation and stability allows geochemists to interpret depositional environments, chemical evolution, and potential extraction challenges, turning seemingly inert material into a detailed narrative of the physical and chemical forces acting over millions of years. Occasionally, subsurface fluids escape along fractures and react with oxygen, producing spontaneous flames or smoke at the surface. These fiery expressions fascinated early humans, who often integrated them into myths and religious stories. Today, geologists interpret such phenomena as indicators of subsurface pressure, chemical composition, and fluid migration, turning once mysterious natural spectacles into measurable data about deep energy reservoirs. Hydrocarbons trapped beneath salt domes can migrate along minuscule fault lines, forming isolated pockets of dense liquid. These structures are both challenging to map and rich in energy content. Understanding their geometry, pressure conditions, and chemical diversity allows engineers to design extraction strategies and scientists to interpret the geological history of subsurface fluid migration, revealing the hidden complexity of naturally confined reservoirs. In some coastal plains, sticky black residues form where evaporation concentrates slowly seeping fluids from shallow reservoirs. Microbial communities colonize these surfaces, metabolizing complex hydrocarbons and producing chemical byproducts. Studying these sites provides insight into microbial adaptation, surface chemistry, and long-term stability of energy-rich fluids, demonstrating that even minor surface expressions of petroleum can serve as valuable windows into the hidden life and chemistry of deep reservoirs. As our journey through the hidden world of oil comes to a close, allow yourself to sink even deeper into calm. Feel the enduring patience of the earth, the layers of time holding their quiet secrets, and the soft presence of energy that has traveled through ages to touch our world. Let your thoughts gently fade, your muscles soften, and your breath flow naturally and effortlessly. Rest here, fully supported in this safe and serene space, carrying with you the sense of connection to the ancient earth and its subtle treasures. If you enjoyed this relaxing moment, please consider leaving a like, subscribing, and turning on all notifications so you don't miss any of our future videos. But for now, let your body relax, release any tension, and allow your mind to drift. Good night and sleep well.